My name is Kenny Hunt, and I will be presenting a talk on procedural fantasy map generation for the purpose of motivating graph traversal algorithms in CS2 courses. Now, graph traversal algorithms are commonly taught in a CS2 course or perhaps an analysis of algorithms course, and the most common of these algorithms include breadth-first traversal, depth-first traversal, and Prim's minimum cost spanning tree. And these algorithms are typically motivated by their application in other domains such as computer networks, the flow of water through a system of pipes, or oil flow through an oil refinery, electronic circuit design, or even more recently in the GIS circles, map-based path planning. Now, these application domains are, of course, quite vital within their field, but can be a little bit difficult for outsiders to engage with. For example, how might you visualize the way in which the algorithm works on circuit analysis? How would you depict, for example, the edge cost of a resistor? Or with respect to the flow of water through a pipe or petroleum through an oil refinery, how would you depict the capacity of the pipe? Thicker lines perhaps equaling more capacity? Procedural terrain and map generation provides an alternate example, and I also believe that it provides good visualization of the underlying algorithm that you're trying to depict. Procedural terrain does use graph traversal algorithms. It does yield results that non-experts can immediately engage with, understanding intuitively things like elevation. And it does provide solid visualizations of the underlying algorithms that they motivate. So let me describe the techniques that I have in mind and how they might apply to the context of a CS2 course. First, we'll generate a graph. In our graph, each node in the graph denotes a sample of a terrain elevation. The edges in the graph are merely connections between geographically close nodes in the graph. For our process, we will generate n two-dimensional points. For k of these points, where k is much less than n, we distribute these k points uniformly along the bounding box of our map. The rest of these points then are simply randomly generated in the interior of the map. And after we do this, we convert these points into a graph using Delaunay triangulation. The figure on the right here describes or briefly shows the point cloud that one might construct and the results of Delaunay triangulation of these points. After we do this, we compute the Verneuil diagram of the point samples. In the Verneuil diagram, which is the complement of the Delaunay triangulation, we see that each node is contained within a polygon, and each polygon is formed such that each edge of the polygon is exactly midway between the two nodes that it connects, or the two, I should say, points that it connects. Now, this polygon map, this Voronoi diagram, yields quite frequently overly randomized clusters of points. That is to say, the variance in the polygons is overly great in most cases. As such, we typically will then relax the Voronoi diagram to produce more uniform and regular results. The Lloyd's relaxation algorithm is quite straightforward. It works in the following way. For each polygon in the Voronoi diagram, we compute the centroid of that polygon. We then move the corresponding sample to the center of that polygon. And this process can be repeated as often as desired. With each repetition, we produce a more regular mapping. After this, we then go to establish a terrain elevation, a sample of the elevation for each node in our graph. So nodes correspond to the elevation of terrain locations, and we need to generate these elevations procedurally in a manner that approximates a physically plausible topography. Now, to do this, we're going to use a simple application of breadth-first traversal. For this process, we will choose a starting node, vStart. We will then, from that starting point, spread out among the nodes in our graph. And for each node we visit, we apply a visitor function. The visitor function's purpose is to establish an elevation for that sample or that node. In this slightly altered version of the breadth-first traversal, you can see that our algorithm accepts three inputs: the starting vertex, the visitor function, but we also pass in a can-visit predicate, which arbitrarily excludes some nodes from the graph. We pass that in to, for example, prevent visiting underwater nodes if one desires. But in iterating through the algorithm, this is a simple breadth-first search algorithm. It uses a queue in which to store nodes that have not yet been visited. And while the queue is not empty, we remove the next node in the queue. We effectively visit it, and we accumulate the parents of each node in a parent map as well. The visitor function for our purposes is the function that creates the terrain, and so let's focus our attention on that for a moment. You can write a variety of different visitor functions, but for our purposes I will describe one that does generate reasonably plausible topographic shapes. It's a stochastic function that is parameterized or can be parameterized on the starting elevation, the ending elevation of the feature you are generating, the amount of variance of this feature, and the size or radius of this feature. Now please note that in this denotation, the radius is not a Euclidean distance, but rather effectively the path length from the starting vertex to, in a sense, the final vertex that one might visit in a radial traversal of that feature. The elevations are generated as a sequence of elevations such that the kth elevation is generated from the previous elevation multiplied by some term that provides an approximation to, a rough approximation to, an exponential decay function. While I won't go through the details here, I will simply indicate on the next slide that this visitor function does inject white noise riding atop a continuous exponential decay. So that if one were to, in a sense, unwind this function, stepping through 50 iterations of this sequence, you might achieve the line given in blue in the diagram on the right, where a closed form exponential decay would smoothly decay across those same 50 samples as shown by the red outline. Now the randomness and the parameters are sufficient to generate plausibly realistic elevation profiles ranging from mountains to continents to plateaus. It just depends upon the settings that one might choose. Here's a visual depiction of the use of this generation technique, where we have repeatedly applied breadth-first search to generate numerous terrain samples. In this picture, the higher the elevation, the lighter gray the color. Blue denotes any sample that is under an arbitrary user-selected sea level elevation. And the darker colors represent those terrain elevations that are above sea level but closer to sea level. Now a map will involve, for our purposes, cities on the map, and for our map we assume that the graph contains layers of data that we don't describe in this paper other than the elevation, but consider assigning, for example, an annual temperature or an annual rainfall to the various nodes in the graph. And other possibilities might include mineral resources or fecundity. And the combination of these properties then will yield what you might consider a desirability rating for each node. The desirability rating simply captures the notion of how desirable is it for someone to live there. So the desirability rating takes into account whatever factors one might imagine. After you rank by desirability each vertex in the graph, then you can, starting from the highest desirability rating, filter the samples and select the most desirable samples to consider as cities. Alternatively, you can simply have users manually choose the locations of the cities they would like to place. After creating cities, these cities are typically connected to roads via a network of roads. And so we have an algorithm. We can apply Prim's algorithm to find a plausible road network that will yield visually appealing and intuitive results. And so while I won't describe Prim's algorithm in too much detail, we simply say, for example, that for each city descending from most desirable to least desirable, we apply Prim's algorithm to that city as the start vertex. And with respect to the algorithm itself, we generate a road network as the outcome. In this particular case, the visited set holds those nodes that we've already looked at. The parent map is the result. The entire graph that results from this algorithm is contained within the parent map. Given a node, you know where it came from in this algorithm by looking at the parent map. Now, the cost of an edge is actually given as effectively is given as the length of that edge in combination with the gradient or the grade of that edge. Simply meaning that you would rather travel on straight, flat, short edges than long edges that climb or descend a great deal. Here's a very coarse look at a road network. In this particular case, you can see that the cities we've selected are highlighted in red. They are connected via the yellow edges, one to another. And the roads tend to avoid steep inclines. They tend to like moving along paths that do not change in elevation. And they do try their best to connect cities in as an efficient manner as possible, as you can see. Now, after we've done this, we might perform segmentation or clustering algorithms to identify things like continents or nation states or regions of the map that we would like to isolate. But we can do this by using, for example, even a breadth-first traversal algorithm, revisiting that. We can select, for example, we can actually do this for all vertices in the map that are, for example, above sea level. Once we have visited a vertex, we can assign it to a continent. And after assigning all vertices to some continent, we have identified all continents, for example. This algorithm can also be adapted to do the same for, say, nation states. Now, in conclusion, I would just like to mention that procedural map making provides a motivating domain for learning graph traversal. It is intuitive in the sense that we all have an understanding of where roads want to go, and we all have an understanding of terrain features. It does provide also a reasonable visualization of the topics of interest. Road networks, for example, flow along low-cost edges, and that can be easily seen in the graph or the map that you generate. And it's also the case that these algorithms can be run in real time in a course level in a browser using JavaScript. Also, by way of mentioning, I will just mention that you can generate very high-quality maps using these techniques, but that's beyond the scope of our paper. This map, for example, illustrates a completely procedurally generated map completely done at random. No human interference was done to generate this picture. Now, I would like to just briefly illustrate this done in the context of a web browser. Here, for example, is an application that follows the outline of this paper. Here I've generated 1,000 random samples in the context of a map. I can then connect them via Delaunay triangulation. There we have it. After which I can highlight the Voronoi diagram. There's the Voronoi diagram. You might notice that there are clusters of samples that are relatively close together and other areas which are less dense. So we can relax this map, I should say this diagram, to achieve more uniform outcomes. Now, once we've done that, we can begin to create terrain elevations on this, choosing, in our case, to make a feature that is a radius of 250. It's a mountain. The height of the starting point is 100, and the roughness, the roughness is a half. Variance is 0.45. So let's see. There is one such feature, and we can begin to combine features, as you can see. In addition, we can create or locate cities. Put one up on a mountain, and we can generate roads. Thank you for watching.